Your brain is amazing. For example, as you read the outline of this video, your eyes move in saccades, French for jerks. Your eyes stay fixed for about 150 to 400 milliseconds, and then they move in about 20 to 35 milliseconds. In general, your eyes jerk forward to the next text, but occasionally your eyes skip over short common words, and about 10 to 15% of the time, your eyes jerk back to previously read text. Similar saccades happen when you look at a face. However, oddly enough, if you look at your own face in a mirror, you won't see saccades because the brain ignores information about incoming light while the eyes are quickly moving. In addition to all this eye movement and all this switching on and off of processing of incoming light, the millions of photoreceptors in your retinas see only a very small section of your field of view, as if they were each looking through a very narrow straw. Yet when you are reading, you perceive all this disjoint and chaotic information as a single coherent concept, words. Your brain has solved the binding problem about words. The binding problem is what neuroscientists commonly call the task of merging lots of information into a single coherent concept. But perhaps it should instead be called the binding mystery because we don't yet fully understand the details of how it works. However, your brain has solved the binding problem for every concept you consciously think about, and it appears that our brains are best at solving the binding problem when our attention is allowed to freely wander among related concepts. For example, imagine being at a farmer's market stand and picking up a perfectly ripened peach. You can move your hand around to see the peach from different angles. You can feel the texture. You can slightly squeeze the peach to check how firm it is. You can even bring the peach near your nose to better smell it. All this information about the peach naturally fits together. It is all consolidated. It all makes sense. Your brain has solved the binding problem about the peach. The premise of this essay is that the reason so many people have difficulty solving the binding problem about math is not because they somehow do not have the ability to solve the binding problem for that one particular topic. Instead, it is because the information about that one particular topic is so dispersed. In other words, if the information about a peach was as dispersed as the information about math, you would be confused about what a peach is. This essay proposes two improvements to math education, MOP and POP. That is, a map of polynomials with the acronym MOP, and a graph of perspectives on polynomials with the acronym POP. Here is the proposed map of polynomials, consolidating information about several well-known series in mathematics. The proposed map of polynomials shows where the series are relative to each other. In contrast, the graphs of perspectives on polynomials show the why, the how, the what, the who, and the when perspectives. Details about the contents of this graph of perspectives will be covered shortly. However, in this introduction now, I'll just say my personal favorite perspective on the geometric series is the what regarding geometry perspective in the fourth quadrant, because it introduces the remainder of the partial geometric series as a little triangle. Prior to this geometric perspective, I was familiar with the geometric series remainder, but I never imagined it had a shape. Of course, a map of a place does not imply everything is known about it. In deference to the typical map makers 400 years ago, who commonly drew imaginary sea monsters as a way of representing the mysteries far from shore, I've drawn an eye of an imaginary sea monster named Ivan peeking out from behind the map's legend to represent the things I don't yet know about the space of polynomials. Like a good news story, the proposed map of polynomials and the proposed graphs of perspectives on polynomials answer the questions of why, how, what, who, when, and where. However, math education is too important to approximate with a news story analogy. Instead, we should try to understand the mechanistic details of how we solve the binding problem about math. And for me, that is a task made more difficult by my ignorance. To be clear, I am not a neuroscientist. I am also not a mathematician. I am also not a teacher. I am a software engineer who happened to recently improve my own mental organization of math concepts. In this essay, I attempt to use what little I know about neuroscience to explain what worked and why. As a starting point, a quick jargon-free overview of the human brain might be helpful. The next section is that overview in the words written by Jeff Hawkins from his book, 1,000 Brains. Jeff Hawkins and Numenta were gracious in giving me permission to include the quotes and figures here. Here is a silent slideshow of quotes from the book 1,000 Brains by Jeff Hawkins. Each slide is shown for 5 seconds, just long enough to quickly scan the slide so you can pause the video if a particular slide catches your interest. A very useful reference frame has 3 characteristics. It is actionable, simple, and hierarchical. Referring back to the book 1,000 Brains, here are quotes about why those 3 characteristics are very helpful. Okay, with that background about why the brain learns the most when using reference frames that are actionable, simple, and hierarchical, let's take a short tour of the proposed map of polynomials, and let's start that tour at the geometric series. The geometric series, expressed in matrix form, is here. The coefficient A can be any real value, which can be thought of as 1 degree of freedom for coefficient A. Similarly, the geometric series common ratio R can also be any real value, which can be thought of as 1 degree of freedom for common ratio R. Therefore, on this map, in which the distances are measured in degrees of freedom, the geometric series is located here at 1 degree of freedom on the common ratio axis and 1 degree of freedom on the coefficient axis. A subset of the geometric series is the converging geometric series, which has a closed form, the coefficient A divided by the quantity 1 minus the common ratio R, if the common ratio R absolute value is less than 1, which we will soon derive in a couple different ways. In turn, a subset of the converging geometric series is the geometric series that converges to an infinitely repeated pattern of decimal digits, for example 0.123, 123, 123, and so on. And the formula for that subset of the geometric series is here. So these three types of geometric series are clustered together, one inside another if it is a subset of that other. Nested subsets are one of the two hierarchies illustrated by the proposed map of polynomials. The other hierarchy is the deeper perspectives associated with the four series clusters. For example, the geometric series cluster is labeled A in the map of polynomials, and that is associated with the geometric series perspectives on polynomials. The map of polynomials shows where the series are relative to the other series, and the associated perspectives on polynomials give short descriptions about the polynomial. Why is it good to know? How is it calculated? What is its algebraic interpretation? What is its geometric interpretation? And who had historic insights about it? All this jumping around, for example, going between the matrix form of the geometric series and the expanded form of the partial geometric series, may at first be a little disorienting. However, it is intentional. Recall the saccades of your eyes as you read text, and recall how you quickly shift your attention between different senses as you hold and consider a perfectly ripened peach. The claim here is, as you are guided to wander among the relationships in and between the different hierarchies, your brain is encoding those relationships. You are solving the binding problem. Evaluating a teaching method is notoriously difficult. I was hoping evaluating the proposed map of polynomials would be a little easier, because there happens to be a Wikipedia article about the geometric series and another Wikipedia article about the geometric sequence. The two articles are similar enough there has been a long-standing debate among Wikipedia editors about whether or not the two articles should be merged. Although I have stayed out of that debate, I thought the two similar articles might be a way to objectively evaluate the proposed map of polynomials by showing it in one article, the test article, not showing it in the other, the control article, and monitoring the Wikipedia view analytics to see if the presence of the map of polynomials changed viewing statistics. Note that in the last couple years, the number of monthly views of the geometric series and the geometric sequence Wikipedia articles have both decreased, but I suspect that is due to COVID-19 related school disruptions. Toward the goal of an objective test of the proposed map of polynomials, for a couple years I've broadened the geometric series Wikipedia article by expanding the section on historical insights and making references to the Taylor series, the Fourier series, and the matrix exponential. Finally, last month I added the image of the proposed map of polynomials to illustrate the relationships between the geometric series and those other reference series. A couple Wikipedia editors viewed the map as original research and removed it, while keeping the added references about the other series in the article. I don't believe there are any concepts on the proposed map of polynomials that are less than 100 years old. I think of that map as a compact cheat sheet, not original research. If you have some experience editing Wikipedia pages, and you have some ideas about how to improve the geometric series Wikipedia article, which, by the way, during school months typically gets over 1,000 views per day, please post your ideas at the Geometric Series Wikipedia article talk page. Referring back to page 81 of 1,000 Brains, becoming an expert in a field of study requires discovering a good framework to represent the associated data and facts. There may not be a correct reference frame, and two individuals might arrange the facts differently. Discovering a useful reference frame is the most difficult part of learning, even though most of the time we are not consciously aware of it. That last part, about most of the time we are not aware of the most difficult part of learning, is troubling and true, at least for me. While in school, I don't recall ever thinking about the mental models I was using. Thinking back, my mental models were probably based upon some combination of how the topics were arranged in textbooks and how the classes were arranged according to prerequisites. Whatever my mental models were, they were actionable in that I could quickly find a topic in my textbooks, and they were hierarchical in that I knew what classes were required before taking other classes. However, I don't think my mental models were simple. I slowly stumbled upon the proposed map of polynomials while considering a geometric interpretation that confused me. Although I suspect I won't stumble upon another mental model that is as actionable, simple, and hierarchical, I know where good mental models are most needed, at the biggest information messes. For example, is the information from cable news actionable, simple, and hierarchical? Based upon recent progress in neuroscience, in this video I have proposed a map of polynomials as a mental model to promote expertise in one area of math. For other areas of math, if you know of a mental model that is actionable, simple, and hierarchical, please make a video about it because current math education needs the help. Brains thrive when immersed in information, provided that information is actionable, simple, and hierarchical. When math information is structured like that, students will learn math by freely wandering around in it. Their brains are wired for it. 160 years ago, Emily Dickinson got it right in the way she poetically described the human brain.
The brain is wider than the sky. For put them side by side, the one the other will contain with ease, and you beside. The brain is deeper than the sea. For hold them blue to blue, the one the other will absorb as sponges buckets do. sight of God. For half them pound for pound, and they will differ if they do, as syllables